So we have one final problem to address with the differential equation, and it relates to this idea right here. So recall that if s of t is a position function, then the velocity is just the derivative of the position function, and acceleration is just the derivative of the velocity function. And so we're going to be using a differential equation to now talk about the actual position function. So of course it's also the second derivative of the position function. So we're going to solve actually a second degree differential equation, because we can say that if we have an object that's falling, when an object's falling, we know two things here, at least on Earth, and as long as we're near the surface of the Earth, that things fall, if you're in metric, at negative 9.8 meters per second squared. If you're still using English units, at negative 32 feet per second squared. Okay. So we know the acceleration, and we're also going to know the following little bits of information. So if we know the acceleration, which we do, it's one of those two numbers, again, as long as we're close to the Earth. Now, if you're further away from the Earth, if you're on some other planetary body, asteroid, the moon, something else, some other object out in space, the gravity is going to be different. You're going to have a different value, but again, it's typically going to be fixed. It's typically going to be fixed. I shouldn't say typically, because the only place where it may be different is if you're around a black hole or something. We'll not get into that. We'll also know how fast it was going when our problem starts. And we'll also know its position, which in the case of a falling object would be how high above the ground is the object. Or, is it below the ground when it starts? Okay. Now we take acceleration towards the Earth to be negative. That's typically how it's done. But you could definitely set it up with acceleration being positive, and then distance away from the Earth being measured as negative if you wanted to. But we typically do it this way. So I'm going to do this in terms of the metric system just because the numbers are a little bit nicer, that's all. Acceleration is negative 32. Now I could say let's solve a second degree differential equation, but I'm going to kind of do it in two steps. I know velocity is the derivative of, or the acceleration, is the derivative of velocity. So velocity is an antiderivative of acceleration. So I know that v prime of t is also negative 32. Typically we don't write it as v prime, we typically write it as using those differentials. So we'd say dv dt is a negative 32. dv dt is a negative 32. Right, from which we can now proceed to solve. Well, hang on, cat's got my tongue here. Now s prime of t, s double prime of t would be negative 32 as well, which would lead us to, again, this second degree differential equation. I completely forgot how I laid this out. I apologize for that. So we could think of solving this second degree differential equation, but the easiest thing is to solve for the velocity in this case. Once you know velocity, then we can go back and find position, and that's what we're going to do. So we begin with our, excuse me for 1 second, apologize for that error. That's one of the drawbacks to writing this stuff out ahead of time, which I was kind of forced to this time because there was a issue the original had with the audio. So apologize for that. So our problem is dv dt equals negative 32, and then we just begin. Isolate them. dv equals negative 32 dt. Integrate both sides. And integral of dv is v. Integral of negative 32 dt would be negative 32t plus a constant. And so now we have a general solution for velocity. But we don't want a general solution. I want an actual know the velocity. So we can go in here and say, well, I know the following. I said that my initial velocity was v0. My initial velocity was v0. So v of 0 is v0 And so V0 would be negative 32 times 0 plus C, in which case V0 is equal to C, or C is equal to V0. So we get a particular solution for our velocity now, which would be negative 32t plus V0. So now we have velocity. Now position is the derivative of velocity, so I can write down this differential equation. ds dt is negative 32t plus V0. Once again, move the t's over. Now technically I should have that negative 32t plus V0 in parentheses. Typically people don't write that out. We just get lazy and a little sloppy there. So we integrate both sides. Integral of ds is s. That'll be negative 32, and then integral of t would add 1, which will make it a 2, so we got to divide by it. So we t squared. V0 is just a constant like 5, so if it was 5 there, it would be 5t, so it's going to be V0t. And then don't forget the constant of integration plus c. So now you can simplify that, and that would be a general solution for the position. But see, we want to know the actual position. So real quickly, let me just clean that up. So now I have my general solution. But we know that at time 0, we are S0 feet above the ground. So we plug S0 in for S, 0 in for T. And we do so. So we find that C is equal to S0. And so we can then write out our full differential equation. S of t is equal to a negative 16t squared plus V0t plus S0. Okay, and that's where that familiar position function that you've dealt with in algebra and earlier in calculus comes from. Now S0, that's kind of the physicist way of writing position. I'll be honest, when I deal with this, since it's height, I prefer to write h of t. Oops. Sorry about that. And have h of t is equal to negative 16t squared plus V0t plus h0 when I'm talking about height above the ground. But this same principle could apply to scenarios where your acceleration is not constant, where your acceleration varies. You could still talk about finding a velocity function and then finally a position function. So that's another example of a differential equation. In fact, it's an example of a second order differential equation. Alright, that's everything. Hopefully this helps you as you get ready to talk now about a little bit about differential equations. And again, indefinite integrals and antiderivatives in general.